When we look at a rigid body, so a rigid body is defined as a shape where the distances between all the massive objects stays fixed. So it's not flexible. The dynamics that govern a rigid body now include the possibility for the object to rotate in addition to the object to move. And typically objects will be able to obviously move and rotate. And we want to introduce in more detail the rotation part. This chapter, by the way, chapter 12, is also very important for statics. Certainly the concepts of forces and work is important for statics, but this is also where we introduce the chapter of torque, and we'll do that in a later video. So this lecture is about moment of inertia. And before we introduce moment of inertia, I want to introduce something called center of mass and comment on some of that. So the center of mass is defined component-wise for an object. So the x component, sometimes it's denoted by a bar. The book sometimes uses a subscript cm. So the center of mass in the x direction for a rigid body is 1 over the mass times the summation of all the masses times their coordinates in the x direction. And then similarly in the y direction, 1 over total mass times the summation of masses at their y coordinates. And of course, this generalizes to total mass times the center of mass vector equals summation of individual masses times their individual positions. These are just 2 components, but we can have it in 3 dimensions as well. It's a weighted average. Sometimes we call it a weighted average because the center of mass is going to be more closer to larger objects, obviously. And so here's a quick little example. I'm going to call this thing a widget, and we're going to be using it several times in calculation. So it's a triangular shape. 100-gram mass on the left, 200 on the right, and then 300 up top. So this 300 grams, lower corners 200 grams, and then lower left corner is 100 grams. Might be a good project to build something like this. The horizontal part is 8 centimeters, and the vertical part is 6 centimeters. This is an example of a triangle that's a 3-4-5. 3-4-5 is one of those triangles. It's always important to know those factors. So instead of 3-4-5, it'd be 6-8-10. So this is a hypotenuse is obviously 10 centimeters. So let's do the example to calculate the center of mass of this block, or of this widget or rigid object. The rods are modeled to be massless, which doesn't affect it that much actually. Slightly change it, but in order to calculate the center of mass, we need obviously a coordinate system because we need a position vector associated with each of these quantities. The simplest one that I can think of is just to have the 100-gram mass be the origin. So the 200-gram mass, that's going to be along the x-axis. And then the y-axis will be this right here. Now that we have a coordinate system set in place for this rigid body, we can now invoke the formulas to just find the simple expression. So let's calculate that. XCM is going to equal 1 over 600. 600 grams is total mass. It'll be 100 times 0. 100 grams times 0 plus 200 grams times that is 8 centimeters. And that's not free fall constant, that's the unit grams, plus 300 grams times the same 8 centimeters. Put a close parentheses out there. So calculating that, obviously the 100 0 goes away, and so 200 times 8 is 1600. 300 times 8 is 2400. So those add to 4,000. So you got 4,000 divided by 600, which reduces to 40 over 6, or 20 over 3. Either way you do it, you get about 6.7 centimeters. It's like 6 2/3 is the mixed number, but rounds up to 2 sig figs, 6.7. Technically, these 8s and 6s should have point zeros on them in order to keep the sig figs right. Everything else has sig figs by the book's convention. So technically that should be 8.0, 8.0 and 6.0. Where is that? 6.7. Obviously, it's going to be closer to the 200 and 300 gram masses, further away from the 100. So somewhere right here, that's that coordinate. It goes kind of up like that. That's at the location of about 6.7, maybe even a little bit further. Yeah, I would actually argue that it's probably even further this way. Something like that. Okay, so that is the center of mass in the x direction. What about the center of mass in the y direction? Same calculation. Easier numbers, actually, because 100 or the 200 gram mass now also has a 0 factor to it. So calculating the y center of mass, it's just 1 over 600 grams. Right, the first two are 0, so it's just going to be 300 grams times 6 centimeters, not 8, because that's the y coordinate of the 300 gram mass. So that is simple enough to be 3 centimeters. So if you're graphing that on here, that is strictly halfway at the halfway mark of the triangle. So that's going to go somewhere right here. And you see here we got this center of mass. It makes sense. It's really close to the 300 and the 200 gram masses. Much closer to, much further away from the 100 gram mass. And you see here that in the y coordinate, you know, there's 300 grams, that's 3 centimeters away in the y, and there's also 300 grams, that's 3 centimeters away from the bottom. So that's why it'd be symmetric that way. But look, what equals is, so 100 times 6.7 equals 500 times 1.3, right? Because this distance between the x center of mass and 8 is 1.3. The distance between 100 times the center of mass is 6.7. So the factors are that 100 times 6.7 has to equal 500 times 1.3. Certainly enough, that's what we get within sig figs. So that's another feature about the center of mass. I mean, if the rigid body was instead a continuous object, you would do an integral, and the integral is not that hard. But I want to move on to moment of inertia. Another remark, by the way, before I move on, is that oftentimes in like a calculus 2 class, you hear something about the centroid, the geographical center of the space occupied by a volume. That is the geometric center of this object, which is in general going to be at a different location than the center of mass. If you remember from geometry, the centroid of the triangle is always where these apothems, not opossum, where the apothems like intersect. If you remember something like this from geometry. And that's true for any polygon. but the triangle is special case in general. But the importance about the center of mass for our purposes is that if you throw this thing up into the air, right? So imagine this triangular widget tossed up into the air, so it's turning up while it moves. Its center of mass goes straight up and then straight down, as if the center of mass is just in straight up free fall. So the object, when it's free to rotate, will always choose to rotate about its center of mass. And that's what makes it important for this chapter. That's called free rotation. Objects will rotate freely about the center of mass. And so molecules, like in gases, molecules have the ability to obviously rotate. And so the center of mass, like for a, let's say for like a hydrochloric acid, you got chlorine and tiny hydrogen, right? The center of mass is very nearly in the chlorine. So the hydrogen atom is, for the most part, orbiting around the chlorine atom. And same thing for like the Earth-Moon system or the sun and everything else in the solar system. Free rotation is about the center of mass. Now, that's one type of rotation, okay? There's all sorts of other different types of rotations that we can consider. Just imagine like sticking any part of this widget on a rod, and there's all these different ways that it can rotate. For instance, as I'm going to delete this, you can stick a rod on the far right edge, right, and have it rotate around this y-axis. Actually, it's in this context, it's better if I switch fonts to make the emphasize the axes. All right, I could have the thing oscillate around this axis, that big bold-faced line, heavy weight line. So you can imagine the triangle will just kind of go rotate in and out of the board or the screen, and that's kind of like a problem. That's kind of like a problem that we did. Looks like I have some stray mark up there. There was a problem like this that we did in chapter 8 where this thing was going around and around and around. That's what I'm talking about. So that's one possible way to get the thing to rotate. Another possible way to get it to rotate is around this axis. And so you have it kind of going like this, right? But you could have it rotate around this axis, right? So it'll go like this, right? And you can do whatever. If you assign it to rotate around, say, this center, then it's going to be something like, if that right-hand corner is stuck, or if that right-hand corner is stuck, then as this thing rotates, it'll be something like this. Right? It'll make like a little wind. So the sky's the limit on your creativity of how you can get this thing to rotate. That's where moment of inertia comes in. Moment of inertia is a measurement of how well how easily you can get it to rotate based on the axis, okay? And oftentimes there's a lot of confusion about what moment of inertia is, so let's just remind ourselves what mass is. For that piece, and how do you measure, a very, very basic question, how do you measure the, oops, I'm gonna change my font, it's too big. How do you measure the mass of a box? If I gave you a box, told you to measure the mass, how would you measure it? Again, far away from any scale, and let's say you're even in deep space, so you're far away from the gravitational pull of anything significant. Kind of like that rocket problem. What you would do to measure the mass of a box away from a scale, away from gravity, the answer is actually really simple. You just apply force. And let's say I apply a force of 10 newtons. The property of the mass of the object tells us that the object will respond by accelerating in that direction. Now let's say the magnitude of the acceleration is 5 meters per second squared. well, then that's how you measure the mass. So a measurement of the mass is the application of the force and the resulting acceleration. Make this thing obviously 2 kilograms. Mass is what we call isotropic, like iso and then the word tropic, in that the direction of the acceleration and the magnitude of the acceleration depends on the direction of the force. You push it up and to the right, it'll accelerate up and to the right. Push it up, it'll accelerate up. You push it down, it'll accelerate down. And that number never changes. That's different with moment of inertia. Because if you start applying a force to an object, how it responds by rotating will be different for each force. Right? Simple example, take a door. Right? The door it's got its hinge, hopefully on the far edge, right? If I apply a force on the far other side, it'll respond by rotating, okay? If I apply a force right here, your intuition tells you it's going to be a lot harder to open that door. Your intuition tells you it'll be even worse as I have a couple other stray marks next to it, that it'll be even worse if you try to push it or pull it. And so the magnitude and direction of the force will change how the object responds to the force. And that idea is captured in moment of inertia. So I want to, rather than defining it first and doing calculations, I just wanted to set that straight as to what it means. So without further ado, let's officially define it. We'll do it up here. We'll erase the center of mass stuff. And define moment of inertia. So again, the moment of inertia is defined for a scalar. It's a scalar quantity, at least the book calls it a scalar quantity, that's defined for every specific axis. So that means we're defining R or I. If you have multiple point masses like this, then the moment of inertia I is defined as the sum of the masses times their distances squared to the axis. And so sure enough, we're going to do this example of the widget and calculate different examples of the moment of inertia. What are some examples of moments that we can calculate? Well, we can select any one we want. Let's consider the bottom I sub x. So if we consider this axis, I call it that let's calculate the moment of inertia around that axis, I sub x. That one's pretty easy. And there's no sum of the masses in this term, in this definition. It's just, well, there's no total mass. So the moment of inertia Ix should just be 100 times 0 plus 200 times 0 plus 300 times 6 squared. This is 300 grams times 6 centimeters squared. 6 squared is 36, obviously. 36 times 3, well, that's just like 12 times 9, which is 108. So you get 10,800 gram square centimeters. A footnote on units, the SI unit of the moment of inertia is kilograms square meters. I wouldn't think too much about the physical interpretation of this unit. It's a kilogram square meter. Technically, it's just one of those units that makes the equation correct. So I wouldn't worry too much about that, but you can show in the calculations that we're going to be doing that this equals 10 to the negative 7, or sorry, it equals 10 to the 7 grams square centimeters. Right, so there's 10 million grams square centimeters in in a kilogram square meter. That usually makes these numbers very small in practice, but anyway, we'll just move on. I'm just going to stick with these 10,000 type numbers. That's I sub x. Now let's calculate I sub y. Again, there's nothing special about that axis, but since it goes through that same 100 gram mass, we can consider it. Right? That's the one where the triangle is going to be rotating in and out of the screen about the y-axis. And now it's still 100 times 0, but now it's 200 grams times 8 centimeters squared. Gotta forget this, can't forget the squared. Plus now 300 grams. One mistake people often make is putting 10 right there, when in fact, 300 is still only 8 centimeters away from the axis. That R means distance from the axis. And so you got to be kind of clear on what you mean by distance of a point to a line. It's always this minimum distance, right? You might think, what do you mean distance of a point to a line? Well, it depends on the point on the line. Well, yeah, but that's what we officially mean. So it's going to be 300 grams times also 8 centimeters squared. Eight squared is obviously 64. You can factor that out. So it's 64 times 500. That's 32,000. Which 64 times 5, I mean, that's like 640 times 0.5. So 0.5, as you all know, is a half. So the fact that there's a 32 there shouldn't surprise anybody because we had a 64 and they're 5. Okay, so pause and compare these numbers. We selected two axes, not completely random, but arbitrary axes. And it turns out that just comparing these two axes, again, the object, if left on its own, would like to rotate around its center of mass. But if you constrain the 100 gram mass so that it's possible to rotate one of these two ways, different situations, we see that I sub y, so rotating about the y-axis like this, is 3 times, it's 3 times harder to get the thing rotating than it is to get the thing to rotate like that. And that's the feeling behind moment of inertia, is it's not a force, okay? It's not the amount of force needed, okay? It's not even the amount of mass needed, but it is the technically, well, if mass is defined, if the mass is defined as how much force needed to accelerate an object, Newton's second law of rotational dynamics defines moment of inertia as the ratio of torque needed to change the rotation of an object. This is section 5, which we'll practice problems next time, but the torque, that's the quantity that we'll define, but we recall what angular acceleration is. It's a measure of how the rotation is changing. So mass tells us how a system changes its motion with respect to a force. Moment of inertia tells us how a system changes its rotation when subject to a torque, which a torque is nothing more than a force acted over some distance that's not at the axis. So lots of things to clear up in this chapter. It's a long chapter. Another thing to observe that's interesting is if we consider the z-axis about that point, then that's just the axis that you take from the screen. It's going out of the screen and then into the screen. If we calculate that, you see something interesting. I sub z. Once again, the 100 gram mass still doesn't contribute. Now we have 200 grams times 8 centimeters squared plus 300 grams now times 10 centimeters. Now we do use 10 because the 300 gram mass is 10 centimeters away from this axis going into and out of the page, but it was only 8 centimeters away from I sub y, only 6 centimeters away from I sub x, for the axes associated with those. So this calculation, it gives us 30, or the second one, 300 times 100 is 30,000. Be clear that there's squared terms here, and these squared terms look like these twos are getting jumbled with the parentheses. This second one, or sorry, this first term, 8 squared is 64, times 2 is 128. So we get 12,800 plus 30,000. I know I don't have the units right there, but this adds up to 42,800 grams square centimeters. Again, the meaning of those units, there's some quantities where the meaning of physical meaning of the units isn't too helpful, and moment of inertia is one of them. So 2 remarks about this final answer that we got. It's bigger than both of them. Not only is it bigger than both of them, right? It's harder to get this triangle to rotate this way from rest rather than this way or this way. Oh, it's a 2D picture, so not only is it the largest of the 3, but in this case, it happens to be the sum of the other 2. Right? Because you calculated the moment of inertia around x-axis, moment of inertia on y-axis. Moment of inertia around z-axis tends to be the sum. And so then you ask yourself, is that a weird special result of this problem? And the answer is, of course, no. It's a special case of something we're going to call the perpendicular axis theorem. So I'm going to delete that as we're going to move on to a slightly different topic.